Hello, my name is GilbertMiito from the Department of Biological Systems Engineering, Washington State University in Pullman, and this is my presentation about treatment of dairy wastewater using a low-cost vermifilter technology. So those are the names of my team members, Pius Ndegwa, Femi Alej, and Sifolo Koulibaly. And this will be the layout of my presentation. I'll start with an introduction, take you through the objectives of the study, the materials and methods that we used, the results and discussions, conclusions, and the future works. So just to give you a background, the dairy industry is really one of the biggest industries in the USA, and it has been characterized by a decrease in the number of dairy animals, like the number of animals that are on the farm. But this increase in the number of animals, the decrease in the number of dairy farms is happening at a time when we're having the increase in the size of the individual farms. Like we're having more animals per unit area, which is bringing about regional concentrations of dairies. So we have like a high number of animals in a smaller regional area, which is bringing about very large volumes of manure. So we can't fully utilize all the manure that's happening in these that's being produced in these areas. So this brings about challenges of concerns to the impact on the air and the water quality, because we can have cases of runoff, leaching, which could lead to eutrophication and several other environmental related demerits of concentrated wastewater streams. So the current utilization of this wastewater involves the use on the farms, like for growth of forage crops. So it's used as fertilizers, which is a very effective method for nutrient cycling, but it also brings along challenges of odor, because there's a big problem of odor, and there's also a potential risk of water pollution, as I've mentioned earlier on. So we are thinking of how can this dairy wastewater be put to use, or how can it be treated? So there are several technologies that have been looked at. We've looked at aerobic technologies and anaerobic technologies. Aerobic range from lagoons and oxidation ditches, and the anaerobic will look at energy recovery using anaerobic lagoons and any other energy extraction options. So these are very good alternatives to the reuse of dairy wastewater. However, they are really expensive, and they have a very high space requirement and very high maintenance costs. So there's a technology that's being fronted, which is called vermifiltration. This is a low-cost, environmentally sustainable alternative, where we treat wastewater streams using earthworms in their ecosystems, and we're able to recover nutrients in form of biomass and in form of vermicast. But there's not a lot of research of having this technology implemented on dairy wastewater streams. So the main objective of the study was to evaluate the potential mitigation of the environmental impacts if we installed a vermifiltrator system on a commercial dairy in Washington State. So this was achieved by evaluating the removal efficiencies of solids, organics, and nutrients in the dairy wastewater streams by the use of this vermifilter system. And we also evaluated the potential air emission mitigations. So we looked at the major air emissions coming off from the dairy wastewater streams. So we were trying to assess how did this vermifilter system help in controlling these emissions. So this is a layout of some of the things we did. Right here in the top left corner, you can see a unit that was already constructed. This is a vermifiltration unit with 3,000 kilograms of worms per unit area, and we have an upstream and a downstream tank for the storage of the dairy wastewater. So this is how we picked samples, and from these samples we used the static. This is a static chamber method, and this is gas analyzer and a multi-point sampler. This is what we used for measuring the emissions coming off from the upstream and the downstream wastewater streams. Then we transported the wastewater, the dairy wastewater, to our cold room at 4 degrees Celsius for storage, from which we picked samples and carried out colorimetry to assess the nutrient and the physical properties of the wastewater streams, both the upstream and the downstream. So this is what we observed. We observed that there was a lot of variation because we monitored this for a period of 6 months from July to December. We saw a lot of variation, which is attributed to the different intake qualities of the wastewater, but it's also attributed to the weather conditions, the treatment state of the unit. But averagely, we found that the total solids in the wastewater, in the influent wastewater, were around 5 grams per liter, averagely around 5 grams per liter, but we achieved removal efficiencies of up to 32%. So we are observing highest removal rates of 32%. With COD, we are looking at averagely 3 grams of COD per liter in the influent, but this was able to be reduced by 51% just by the use of this vermifiltration technology. Total nitrogen was standing at 600 milligrams per liter, but with our technology, we're able to reduce it by up to 91%. Total ammonium nitrogen, which is like the most soluble form of nitrogen in the wastewater, was also found to be at average around 200 milligrams, 200 parts per million. And with our treatment technology, we saw that we're able to achieve up to 90% of the removal efficiency. So we were able to confirm that this removal is attributed to the degradation of the organics, which is occurring in the vermifiltration, and also the ammonification, nitrification, and denitrification, which are occurring concurrently. That's why we are able to see the high removal efficiencies of up to 90%. So we went ahead and also looked at the total phosphorus. Total phosphorus was approximately around 60 milligrams per liter, and we were able to remove up to 57% of it using our treatment technology with the worms. The orthophosphates, which are like the most reactive form of the phosphates in the wastewater, were up to 20 milligrams per liter, but we were able to remove 30% of this. And we attribute this removal to the filtration effect, because the vermifilter is able to carry out a filtration process, and there is also oxidation of the phosphorus that's present in the dairy wastewater. So we are confident that the vermifiltration unit was able to achieve these removal efficiencies. We also looked at the emissions using our static chamber method, and if you look at ammonia, there was not a lot of ammonia coming off of the dairy influent, because we are looking at an average of around 0.3 parts per million per minute, but still we were able to reduce this to as far as 100%. Like we're able to achieve up to 100% of the removal efficiency. So we are saying that the units, the downstream wastewater had almost no emissions coming off. When we look at carbon dioxide, which was around 30 parts per million, averagely 25 to 30 parts per million, we are seeing reduction rates of up to 85%. If you look at this, 85% of the removal efficiency. So we're able to get rid of 85% of the emissions. Same thing applies for methane, which was around 5 parts per million average in the influent. We're able to reduce it by up to 100%. So we are saying that almost there were no emissions coming off in the wastewater downstream. Yet upstream, we are seeing a bit of concentration. With the case of nitrous oxide, these values were so low that this variation is probably attributed to just instrumental errors, because the values were almost less than 0.05. So there was a lot of variation in this that we didn't put it a lot into under consideration. When you take a look at this, we try to assess. We also kept monitoring the temperature just to see if it has any effect on the removal efficiency, and we observed that for an example of the nitrogen formed, which is ammonium nitrogen, there was up to 71% correlation between the temperature and the removal efficiency, implying that at higher temperatures we are having higher removal efficiencies. This is because at higher temperatures we're having more activity happening in the vermifilter, so that's why we have this high correlation. Same thing happens to ammonia, which is in form of emissions. Up to 83% there's up to 83% correlation between the temperature and the removal efficiency. So still we can appreciate that at higher temperatures, higher ambient temperatures, we are getting more removal of ammonia in form of emissions. And ammonia is like the biggest issue with dairy wastewater streams. So this is giving us good progress that the vermifilter is actually doing removal of these nutrients and the reduction in the emissions. So in conclusion, the vermifilter system was able to remove a significant portion of the nitrogen and the ammoniacal nitrogen with up to 91% removal, but there were moderate removals in the chemical oxygen demand and the total solids. Also, the total phosphorus was fairly removed, up to 57%. And from the study, we can appreciate that this reduction in the organics and the nutrients is due to the synergistic action of the earthworms and the microorganisms present in the vermifilters. In regards to emissions, we are seeing up to 100% of reduction in upstream emissions coming off from the dairy water, and we've also seen that the prevalent temperature can influence up to 83% of the removal efficiency. So temperature has a lot to do with the efficiency of the technology. And we've also observed that the vermifilter is not very conclusive on nitrous oxide emissions, so we need further investigation into this. But we're able to conclude that a vermifiltration system can reduce the organics, the nutrients, and the potential emissions coming from the dairy wastewater streams. So currently, we are still investigating the effects of adjusting the organic strength, the hydraulic loading, and we're also looking at adjusting the earthworm density, how it affects the removal efficiency. And we're also looking at determining if the irrigation frequency has something to do with the removal efficiency. These are all undergoing works. Thank you very much for your time, and I appreciate you for listening. Have a good day.